That is not what I wanted to do. Maybe it is. Cool. Okay. Hello. Oh no. Am I going to have to? All right. Good afternoon, Matthews. Hey, how are we doing? I was hoping to start without having to inflict that upon you, but there it is. Once again, welcome back. My name is Jashank. I am a terrible impression of your usual rainbow head lecturer who is unfortunately waylaid today. So, before I get on to what we're going to talk about today, the usual bump applies. Please don't panic. It's extremely unsettling. So please avoid panicking, but instead be aware that there is a second assignment. It's coming up real soon. We're going to have a spec for it sometime later today into tomorrow, and we'll be discussing that tomorrow during the lecture. So stay tuned for that. There's also a weekly test that's due tomorrow at midnight. So if you haven't already done that, have a think about doing that sometime soon. Also, challenges for week 6 got extended because all of you seem to love breaking codes. So there they are. And finally, and most interestingly, there is a quiet week. Because why not? It's a busy semester. You all have full course loads. You're all busy. You've got other assignments. So we give you a quiet week from us. We don't inflict anything on you for that week. There's no lectures, no tutes, no labs. The help sessions are still running if you are looking for some assistance. All right. So let's talk about what we're going to be looking at today. So what have we seen recently? We've seen how to manipulate data in files. We've seen how to manipulate data in memory with pointers, with our references. And we're very nearly at the end of the C syntax that we're going to show you. There's very little left in terms of actual syntax. And I think after today, there is no syntax left. We'll get through all of the remaining C syntax that you're going to need for the rest of this course today. Because knowing a language, how many, just out of curiosity, how many of you know many languages, more than one? The human languages. How many of you know more than... I saw a bunch of hands go down when I qualified that. How many of you know more than one human language? How many of you know more than 2 human languages? More than 3? Wow. But as I'm sure those of you who know even anything about anything about the languages, you do know, the one thing you know is this, that even with a handful of words and the knowledge of how to express yourself, the knowledge of how to express yourself isn't important. It's what it is that you're expressing. It's the things you're saying, the conversations you're having. Yeah? So that's what we're going to sort of finish today. We're going to finish the shape of the language with something really, really important that you're going to need really for the rest of the course, which is talking about structured data, composite data. And we'll also talk a little bit about scope, and lifetime we'll talk about dynamic memory. The usual qualifiers apply. Hopefully you get the shape of it, but let's talk about data. We've talked a lot about various different types of data. We've talked about data that is integral. We've talked about data that is real or as close to real as we can get. We've talked about pulling data in. We've talked about moving data around. And really the thing that you probably noticed, although probably not obviously, is that all we're doing is taking data and moving it around. We're taking information and moving it around. And that's why we call this field informatics, because all it is the science of the craft, the art, the beauty of moving data around, changing it, making it do interesting things. And we don't just mean, oh, here's some random 1s and 0s that I picked up off the street. Anything can be data. And when we're working with the data that we have, particularly in C, up to now we've seen a couple of ways of holding a bunch of complex related data together. Yeah? And really all programming languages give you a way to express this idea of taking a bunch of interesting information about a thing and grouping it together, making it one logical unit that you can manipulate. So in C we've seen a couple of approaches. One of the approaches we've seen and we've spent quite a while on is arrays. Hopefully you're now starting to get a bit comfortable with working with arrays and working with initializing, moving data around in arrays. But some of you, in fact hopefully all of you, have spotted the major problem with arrays, which is they don't have size. Arrays don't have inherently size associated with them, yes? There is no size associated with an array. If I just give you an array, I can't get you to tell me how big that array is because you couldn't do that. If I just pull an array out of my hat, it's some size. Cool. They also have this really nasty problem that all of the data I can store has to be the same kind of data, the same kind of information. It has to be a bunch of integers, or a bunch of characters, or a bunch of floating point values. And that's not useful, because when we're talking about real systems, real things, real people even, there is more than just a bag of integers. I'm not going to pull a student apart and just sort of go, okay, here we go, here's some integers, because that's not how people work. That's not how the real world works. Everything is not just uniform blobs of integral mess. Hardware people would like you to think that, but no. There is actual complexity, there is structure, there is shape in the real world, and in C, it's not great to deal with that with an array. So, here is some hypothetical code, which hopefully you can all read. Let me just knock down those room lights a bit. Here's some hypothetical code that might handle part of our student database. Now, I went and had a look. There are there aren't 1,087 students enrolled, there are 1,087 seats in this course, so let's have a bunch of arrays to handle every single student we could possibly have. And all of you have student IDs, so we need some space for that. All of you have names, hopefully. Who doesn't have a name? Fantastic. Thank you for breaking everyone's assumptions about that. Do you know, names are hard. Names are really, really hard. And if you don't believe me, there are, of course, a couple of Tom Scott videos that prove my point, but also consider people who only have one name. In a couple of my classes this semester, I have a student who only has one name, and every single UNSW system that is set up to deal with people with two names, a first name and a last name, and potentially some other names in the middle, they just freak out because there is only one name. So the way you probably want to do names is just, here is a box, put the name in there. Good. And in this case, because historical reasons, you are allowed to be 64 letters long in name and no. Who has a name that is longer than 64 characters? There are a few of you. I don't know who you are because I can't see what your names are. There are tutorials. Every single student will be in a tutorial. There's an assignment 1 mark, which every single student will hopefully now have. Marks are still being mangled at the moment. But now we run into problems like, well, I have 1,087 seats that I can put a student in. And at the beginning of this course, as many of you probably know, all of those seats were full. So, you know, that's great. We've got this array. We're using it to its intended capacity. But now what if I say, oh, this student here, a student number 39, drops the course? Well, what do we do? No. Later. If student number 39 were to drop the course, well, what do we do? Well, probably we have to move all the students down one. We have to shuffle values around. What if something goes wrong? Because things go wrong. This is the real world. Everything can and will go wrong. So we're moving these values down. Our computer catches fire. Perfectly legit. We're moving these values down. The radar at Sydney Airport wipes our hard disk. And if you don't believe that's a real thing that happens, you know there's a door on the side of the library all the way up. And there's nothing apparently there. There's just this door floating in the middle of a wall. That's where UNSW's first computer hard disks was loaded into the very top of the library. Big old magnetic disk would have stored a couple of dozen megabytes. Whoa, big data, yes. And the radars from Sydney Airport kept causing the disk to be damaged. And it took them so long to work out that, disks, damn it, magnets. So student number 39 might drop. What about a whole bunch of students dropping? And what about students joining even? Because, you know, some of these students are going to drop, some of them are going to come in. What if I want to add more fields? Because, you know, presumably we're going to have more than just one assignment. Presumably we're going to give you more than one thing to mark. Presumably we may want to change this tutorial here. This type is useless for something interesting. What if this thing goes horribly, horribly wrong? And the problem here is that we are making an assumption, and that the assumption here is that in index, say, 0 of all of these arrays, we're going to find the piece of information we're looking for, a related piece of information, and that's not great. We're making an assumption about the structure of data in our system, and whenever you are making assumptions about the structure of data, the first thing you should think is, how can I actually express that? So things we want. We want to be able to group a bunch of data that is in some way related. Ideally, that data wants to be of different types. We want to have multiple different things. We want a way of being able to pull out each thing in this unit object blob. And in other languages, you have nice composite types, but C is not a nice language. C is a cruel, harsh language. And so our way of doing this is, well, a little bit strange. But here it is. This is actually my favorite feature of C. This is called the struct. Struct for structure. And it's this way of taking a bunch of data of all sorts of different types, an arbitrary number of different things. I can take all of these things and dump them into a single box, a single thing that has this given type. And I can pull out the little things that are inside this. I can take our values that are there and I can use them and do interesting manipulations with them. So let's grab this student type that we know is terrible in its entirety. Let's grab our student type, let's jump over here, and let's turn this thing into a structure. So this is what we've got so far. We know that we'll have some number of students. Fantastic. We know that a student will have an assignment mark, a student will have a name, a student will have a student ID, etc. So these are all the things that I want to have in my structure. These are all important bits of information. So what I'm going to do is I'm just going to take my structure and wrap it around it. Remember our structure syntax, by the way, here. We start out with something quite weird, 2 magic keywords. Both of these keywords do magical, interesting, useful things. We're going to sort of look at them together for the moment, and we'll look at them separately later on. We have this thing that is a struct, and I say we define a type define, structure, or what are we going to call it? By convention, we call this part, this next part, which we call the tag of a structure, we call that the name that we are going to give our structure. And I just take this bunch of apparently variable declaration sort of things, pop them into my structure. Remember, of course, indentation is important. Indentation rules are important. The style guide has a lot to say on indentation, but the précis is any time you have an open brace, until it's matching closed brace, everything should be indented by 1. And by 1, I mean by 4 columns, which we want you to do with spaces. So I have here my structure, struct underscore student. I have some data that I'm going to store in it. And because typing struct underscore student is really not convenient for me to use all the time, and because structured data is so pervasive in the system, I'm going to say this is actually going to be called student. And this is the name I'm now going to use for this value from here on. This student name is what this type is called. Our type definition says that. Okay, so by convention we keep at the top of our program our hash defines, our type definitions, like this here structure, and then we can continue into the actual meat of our code. So let's have a nice little function here which has a student in it. I'm just going to pull a student out of my hat. And the way I do that is exactly the same as I would pull any other type of data out of my hat. So instead of saying, I don't know, int student, I would say student. And that's a really terrible variable name, so I'll call it S for the moment. So this is me declaring a structure. This is me declaring that I will now have an instance of this structure. So what can I do with this? Well, I have all of this information that's locked up inside my structure here. Wouldn't it be useless if all I could do was just sort of look at it? And it's just sitting there, and I just can't do anything with this. Thankfully, there are 2 new bits of syntax, 2 new operators. I'm going to talk about one now and another one in a moment. But the most important operator when you're dealing with structures is dot. S is my variable, dot, and now I give it the name of one of the things in my structure. Say my student ID. Yeah? And this is what we call an L value, a left value. It can appear on the left side of an expression. Other things that you've seen that are L values, just in case you've forgotten, if I had some pointer, this is an L value. I can assign to it. Even just a straight up variable is an L value. And this, s dot thing, is an L value. I can assign to this. So let's assign to it. I'll just pull a student number out of my hat. Cool. Bunch of random numbers. Lovely. I now want to put a name into this structure. Now this array of characters here, this is a string, but I can't just assign into it because this array in a structure now actually has size. And you can think of it more as just a sequence of boxes up to a certain size. Yeah? I'm going to copy a string into here. And the way I copy a string, who remembers how I copy a string? I heard fgets. Yes. So we've seen a little bit of string.h. And one of the functions that I don't think I mentioned, but it's definitely in string.h, is a function that lets us copy a string and conveniently, because vowels were apparently really hard to find in the 1970s when they named all these things, it's called strcpy, for string copy. And we've built functions, or we probably have built a function that does something like this before. It takes a value in an array and it copies it to another array until it reaches an L terminator. Because that's what you find at the end of a string, right? So I'm going to copy to s.name from, let's pick a name. Just completely randomly choosing names here. We'll give this student a tutorial. We're in tutorial 1. And we'll give them an assignment 1 mark. Missed exactly 1 instance of a time zone. Oh, terrible. So there is our student structure. I have taken my structure, I have put some values in it, there it is. Okay, well that's pretty useless because it's just sitting there. Once again, I can't really do anything useful with this, but maybe I could print out some values that are in it. And in exactly the same way as I would assign to this thing, s dot the name of the field, I can do exactly the same thing to access values in here. So if I were to dig out my good old friend printf and to print out a student ID, let's say, yeah, we'll do it by hand. Has anyone seen the modifiers for printf? Have we talked about the modifiers for printf? We'll leave that for the moment. I'll come back to that a little bit later on then. Now I just want to print out a student ID. Well, that's easy to do. I just say s.student ID. Does help if you can type, of course. But there it is. So I can, in fact, let's just compile this and run it now. This already, well, when I give it the necessary hash include, yes, it will compile and run. stdio.h, string.h. So there's our program. Let me grab that terminal that I have up my sleeve over there. My God, this mouse has gotten worse. Close enough. All right. Whoop, it's called struct, isn't it? Okay. Well, it compiles. What happens if I run it? Okay, I get the data that I put in back out again. Well, that's kind of boring, I suppose, but it's what I expect, yeah? At this point, I could still just go and replace this structure with a bunch of ints and a char array, and I would get exactly the same result. But what's important to note here is that I'm talking about this object, this unique thing that groups a bunch of information, a bunch of properties together. Yeah? I'm composing data. I call this a composite data type. Other languages might call this a record type or a structured type. Some languages don't actually have an idea of this, and you have to sort of fake it by other means. Okay, so let's print out the rest of the things in this structure, just quickly. And again, I would printf name, printing a string, format is %s, yes, thank you, s name, printf tutorial is a %d, printf assignment 1 mark, %d, s assign 1 mark. Cool. So this is all really rather boring, but printing out a student is something that we might want to do often. It's a useful thing. So what do we do with useful things? We wrap them up into a function. So I'll just grab these lines here and move them down into my new print student function. Now what does a print student take? Well, I'm going to need to put a student in here. Can I pass structures as function parameters? Yes, I can. Lovely. So I can just say student s for this function, and there it is. Let me grab that prototype and pop it up here with the other prototypes. Let me put a print in here. I'm going to take my student, I'm going to print it out. All I've done is moved where the prints are happening. I'm putting a function in the way, and when I do that, so it works. Lovely. That's exactly what I want to be seeing. If I were to change this or come up with another student, this would just work fine. So this is how I go about taking a structure of data, putting some values in it, moving those values around into another function. But it's all rather boring to just have one student. So let's have some more students. In fact, let's also give us a way of reading in student data. So the first thing to mention here, of course, is something we already know, which is that if I pass s into my read student function. In fact, let's do that. Let's say we've got this read student function, read student s, and I'll get rid of that for the moment. What I'm going to do is I'm going to read in a student. I'm going to use, let's use fgets to do it. Why not? So the shape of this function would be something like void read student for some student s. Well, I want to read in a bunch of integers. We have a function that does that really well. I probably also want to prompt for input, so let's do that as well. So, a good friend for reading in integer input, scanf. I'm going to scan in a %d, and I'm going to put it into s.studentID. Now, we have a problem here, which is scanf. What does scanf take? Scanf takes a format, something to read, something to recognize. And it takes a bunch of references to put the data it's recognized into. Now, if I just do this s.thing, I pass that into scanf, I have a problem because that's not a reference. So, how do I take a reference to a thing? Yes, I throw an ampersand at it, and for safety, I'm going to wrap that resultant thing there, that expression that I want to assign to, in parentheses. All right, so I have a way of reading in a student ID. Let's quickly duplicate that so we can read in tutorials. I feel like I'm repeating myself here, and this could probably go into a function, but for the moment, we'll leave it here just to make the point. I want to read in a name as well, so I'll use my good friend fgets now. So fgets, once again, needs somewhere to put its data. So I'll say fgets use s_name, a reference to which I have provided to you. But now we have a problem again because s.name is actually an array, and as we know, arrays are implicitly referenced. So I don't actually need to reference s.name. Fantastic, I can just pass it in. S.name does have a maximum length, so I do need to tell fgets that, which I do by saying max namelen, if I recall correctly. It is indeed max namelen. And I'm going to read from standard in. Okay. So I'm going to read in a student. I'm going to print that student out. Good. I'm going to add a prototype. A useful thing to remember, by the way, when you're dealing with large blobs of code, as you will start to be doing when you're breaking things up into functions, it's probably a good idea to have your prototypes reflect the order the functions appear in your file. A sort of table of contents, as you will, of the things that are in this file. I have a main, but I also have these functions, which are going to appear later on and probably in this order. That's a point of preference. It's not strictly enforced, but it's useful to know. Okay, I'm getting an initialization warning. Let me just shut that up. Cool. Let me just prove to you that compiled. Good. So it's now prompting me for some data, so I'll give it some data. We've seen this bug before, haven't we? What has happened here? I've entered my student ID. I've hit enter. Now I should be reading in a name. What's going on here? Sorry, can you repeat the beginning of that? I missed the beginning. Yes. Yes. That's exactly what's going on here. Remember what scanf does? Ah, damn the mouse. Remember what scanf does. Scanf is looking for this. It's looking for a %d. The moment it stops seeing a %d, it just goes, okay, cool, that's it. I can stop reading now. The problem I now have is, well, that's not very useful to me. So what if I go scanf %d new line? To read in that new line as well, let's see what happens. Let me just kill this and recompile and rerun. What's going on here? Waiting for an end of file, good theory, I like that theory. What's going on here? We know what scanf is doing. It is looking for the first thing that ceases to match its pattern. And it just so happens enter is part of its pattern. So I can keep hitting enter and this scanf will just keep going, yep, that's an enter, I'm expecting to see that. So, yes, something like getchar is probably a better bet here. So I'll do this scanf. This is why you should never do scanf %d or scanf anything followed by a new line, because it will go horribly, horribly wrong and explode. Let's just do a get char. Let's throw away its result, because we don't need it. We know it's going to be a new line. Do we? Let's make sure of that. How do I make sure of that? Yep. Get char is the new line character. Well, what can I do? I can't really do anything useful here. I could prompt for the student ID again with a message telling the user to get it right this time. But there's not really much I can do here, unfortunately. There are other approaches that we could use to get this more right, but for the moment, well, all we can really do is just grab that character and we'll just drop it on the floor. So we'll just do that. Let's just grab that character, drop it on the floor, and see what happens. So we're scanf in %d again, and we're getting a character which should hopefully be a new line. And now it works. Now I'm being prompted for a name. So yes, that enter is being left there because the scanf is refusing to recognize it. But now there is a problem because fgets wants a line of input. It's sitting there waiting for a line of input, and it just so happens that if the first thing it sees is an enter, well, there's your line of input. Perfect. Let's keep going after that. Not very useful. So we grab that new line, we drop it on the floor with this get char here, and then we continue along as is. I'll dump in a name, I'll dump in a tutorial, I'll dump in a mark. What? What? But I put those values into my struct. What are you talking about, you silly computer? What's going on here? Let me show you main as well, because we've gone to all of this effort of reading in this data. It's there. We've read it in. But now we have a problem. Where has our data gone? Yeah. That's absolutely right. That data that we've read in, where have we read it to? Structures are weird because structures like integers, like doubles, like straight up chars, like references are copied. They are not passed implicitly by reference. These things are copied. So the copy of S I'm working with in read student, well, it's just that copy. Yeah? To give you an even more minimal example of what's happened here, this would be like saying get int for some int I, scanf into, %d, into I. Well, I now can't do anything useful with the value in I because that value never escapes. The value never comes back to us when we call this sort of thing. It's limited, it's constrained by scope. Yeah? And we'll talk a little bit more about scope later on today, but the first and most important thing to remember is, well, when I have some data, when I want to put that data somewhere, for instance, this scanf here is trying to take some data and put it somewhere. How do I say I want to take some data and put it somewhere? I need me a reference, yes. So instead of reading in just straight to an int, I'm going to pass in a reference. I don't need that reference anymore because that's all that I need. And now I am able to put values into wherever getInt past value was. With read student, then, I can do the same thing. With read student, I need to pass a reference to student. And that will also get rid of this hack to fix this compiler warning. Now I need to pass a reference of read student, of S into read student rather. Pass a reference, give me an ampersand. Now, when we've been dealing with ampersand values before, we had to do something to that value to make it useful again. Yeah? So if I was using this S value down here in read student, well, previously I was just going S dot. Now I need to add something to this. It's already been ampersanded. I now want to do useful things with this. If I have any reference and I want to do something useful with that reference, I need to dereference that, yeah? I need to take that reference, reach through it, and then we can actually do something. So, wrap it in parentheses, chuck a star up the front, and now this looks just like a structure. And I can dot it. And I will dot it. And I will change all of these S's to be star S's because that's what we need here. Once again, here's an S. Whoops. Who's been playing funny buggers with me keyboard? There we go. Other people's computers are so difficult to use. Anyway, here we have our star S read student function. This takes a pointer to, a reference to a structure, and puts values into it. Fantastic! I can now do useful things with this here value. I'll change my prototype. Read student, reads in a student, star, print student, takes just a straight up student, and now the moment of truth, tasting and judgment. Does anyone even watch Iron Chef anymore? Iron Chef, yeah. Well, that's looking much better. I can now take some values, put them into my structure, print them back out again. There is a stray new line there. Why is that stray new line there? F gets the new line as well. So we'll probably want to lop that off at some point. For now, I'm not fussed. There it is. Yeah? So we take some data. By reference, we can read it in, we can do useful things with it. Now, I'm now starting to look at this code and starting to think this code is starting to look ugly. I'm having to throw lots and lots of symbols that require lots of keyboard gymnastics as I am typing this program. If there's one thing that programmers are, it is lazy. The second and third are impatient and hubristic. Programmers are lazy. Programmers don't want to type this keyboard gymnastic sequence of characters just to get a field out of a structure reference. This is syntactically valid. The compiler accepts it, it does what we want, but it's ugly, it's painful to type. So we can do better. And the way we can do better is by introducing a new piece of syntax. And this is it's the last piece of syntax. Give it up for the most boring piece of syntax you're about to see. This piece of syntax is a replacement for open paren star thing close paren dot. It's thing arrow. Whoa. Lots of people call this arrow. I call this stab. Andrew does not like me calling this stab. But I do it anyway. You can call it stab as well, or you can call it arrow. Both of those names are perfectly acceptable for this operator. So we've got two new operators happening here. We've got the new dot operator, which takes a structure, dot a field within that structure, and lets us manipulate that data. We have another piece of syntax which takes structure reference or structure pointer, arrow, field name, and it lets me do the same thing, except all I now have is a structure reference. All right? Let me quickly fix up the rest of these. But do you see how this looks so much nicer than what I would be left with otherwise? Let me show you these two lines side by side. I saved 2 characters! Yes! Ha ha! The Holy Grail! I don't have to type 2 characters. But programmers are lazy, but programmers are also smart. You're going to be doing this. You're going to want to do this. This open paren star thing, close paren dot, field name, a bunch of times. You're going to do this over and over and over again. So these 2 characters that you're saving every single time, and that little readability loss you are taking every single time, well, now we have a nicer, easier, faster way to type this expression that we're going to use a lot. I'll pop that there, just to give you some reference. S stab, S stab, there we go. So, does our program still work? Whenever we make big old syntactic changes to our program, it's probably worthwhile checking that our program works. Cool, it works. So there's 2 very interesting things going on here. The first thing that's going on here is I'm taking a reference to a thing that is low down the stack. It is in main's scope. And we'll talk a little bit more about what that scope thing means in a moment after the break. S is being we're taking a reference to this S thing, we are passing it up. We're taking that S reference that we are holding here in main, we are passing that up into functions that we call. I could do the same thing with print student. There is nothing stopping me from doing that. I could just go through, change all of those places where I'm using S dot into S arrow or S stab, and it's fine, it works, it's great. Maybe you'd prefer that if your structure is big, because remember, structures are copied. This structure, actually, how big is a structure? How big is this structure? There's an operator we can use, and it kind of looks like a function, so I'll say it's sort of a function, but it's actually an operator. We'll disregard that difference for now, and some ISO committee is going to hunt me down tomorrow. I have an operator that lets me say, how big is this thing? So let's wrap up this part of the lecture, this first half, by saying, how big is this structure? Well, here's what our structure looks like. I have 4 integers, 64 characters. I could probably do that in my head, but I'm lazy because I'm a programmer. Or is it because I'm a programmer I'm lazy? But whichever it is, I'm lazy. I'm going to ask for, and this is always available, and we're going to use printf%zu And what a whack new function called size of does is it just gives us the size of the thing we give it. So if I have, say, size of a structure, it will tell me how many bytes that structure uses. I could also ask, if I had a reference to S, how big is that? Because size of's argument is not a value. Most functions take a value as a parameter, but not size of. And there's a reason I'm a little bit hesitant to call it a function, because it's an operator. This thing is able to take types. So let's do that. Let's tell you how big those values are. It will tell me that ampersand S down here is 4 bytes, which is what I would expect. How big is a byte? A byte is 8 bits. 8 times 4, 32. So this here is a 32-bit value. What a surprise, because my system is a 32-bit system. On my laptop, which is a 64-bit system, a pointer would be 8 bytes in size. And this structure here is 76 bytes in size. 64 plus 3 integers, which are 4 bytes each. 64 plus 12, maybe that's 76. Anyway, let us take a break here for, let's say 10 minutes. Give you a chance to stand up, move around. After the break, we're going to have more structures, more lifetimes, more scope, more good stuff. So stay tuned, all that coming up after the break.
Could you put the code up on the website?
I can indeed, just a moment. Sources unmuted, lecture. Welcome back. Let me summon up my code again. Let me kill this. Let me also quickly mention, because I got a bunch of questions about it, where you can find the code that I'm currently working on. I've dumped that onto my website, which is allthewsw.csc.edu.au/tilde/jashankj/cs1511 And if you look at that directory, you will see, yes, my lecture notes, but also down here, struct.c, which hopefully it will try and make me open in RStudio, but there is the code. I will make sure there are links to this up more usefully on WebCMS after the lecture. All right, back to the show. So actually, before I continue, let me just quickly mention three things, that I got a couple of questions about during the break. First of all, I got a good question, which is, in this code here, what would happen if I declared my types after I tried using them? Yeah. So what I've got here is read student and print student are of type student. Surprise, they're student types. And here is my definition of the student type. C is an interesting language because it reads through files as it is compiling them line by line from the top to the bottom. And so a consequence of this is, at the point where I now have these prototypes, what's a student? Because to see, and this is in fact the reason we need prototypes anyway, to see, all it can currently see is this at this point. What's a student? I don't know, not defined anywhere. So it's really, really important to make sure that you do follow this order, which is to have your types before you're going to use them here. Another thing that I got good questions about was, I've talked about that, structure naming. So structures have what we call a tag, and it's just this portion here of the structure name. Struct thing, and then some curly braces, and then some member definitions or field definitions. In this instance, I've used the name _student as the tag. Yeah? What is the significance of this? The significance of this is, well, there isn't one. It's just a name. But I've deliberately chosen to follow this naming scheme, which goes that a structure has a tag. That tag should be _ its type name. Remember that I'm redefining this structure to have this type student. So this student here gives me that this here should be student. Maybe you don't need this. It's probably a good idea to have a tag there, and we'll see some cases where you can't elide the tag later in the course. And the last thing was, a few people got really confused when I went and did this, which was to go size of student star. And that is because, as I sort of confused you probably all with a bit, size of is not a function. Size of is an operator. Hopefully that will stop the ISO committee coming after me. Size of is an operator. It takes a type as its argument here. Here I'm giving it the type, student star. This type is a type. When a star appears in a type, this is a reference type. This type says the value I will hold will point at a thing. But it is not a thing itself. This star here in the type position means something very different to an operator star. Yeah. Remember, the operator star is the inverse of ampersand. The operator star is dereference a value. Yeah? Okay. So those were the main questions that came up during the break. Are there any other questions about structures? Yo. Can I refer to it as underscore student? What a good question. The answer to this question is, let's try it and see. I'm going to go with no. The reason for this is because underscore student by itself doesn't actually mean anything, because it's a structure tag. And to refer to a structure by its tag, I need to say struct tag and then thing. And now you start to see why I use a type definition. The type definition means I don't have to say all of the struct underscore student stuff. I can just say student. All right? Go. Sorry, you said two words there that I don't understand. Can you add methods to classes? What's a class? Right, can I add, okay, what's a method then? So here's the thing that some of you coming in from other languages will have seen before. If you haven't come in from another language, you can now ignore the next few moments. In other languages, there is a mechanism for strapping some data onto some associated methods. And we call this a class in most languages or something of that nature. C doesn't have them because we're grown-up programmers. We don't need training wheels. We can know that a thing taking in a student reference and potentially called read student is probably about students. Probably about this type called student. When we see later in this course, the closest you will get to something that resembles an object in a class in some whiz-bang object-oriented language, you will see exactly why it is a bad idea. All right, for those of you who don't program before, or haven't programmed before, haven't seen other languages, haven't been corrupted by their evil, welcome back. Let's go back to the story for a moment. And let's talk about something that we've seen before. So for the back half of this lecture, we're going to talk about lifetime and scope. And what I mean by, well, let's step sideways for a moment. Let's talk about the stack. Yeah? We've talked about the stack before. We know roughly what the stack looks like. I say this because I'm currently a little bit annoyed because my diagramming tool fell over. So we know what is in a stack frame. We know it holds information about where the previous stack frame further down the stack is. It holds information about where the program is going to continue running from when this function finishes. It holds information about local variables. It holds information about parameters and return values that are only relevant for this invocation of this function, yes? When I call a function, it sets up its stack frame. And it says, here is some information that I'm going to need for this function to execute, to do something useful. And as we saw earlier, when I have data that is constrained to a function's scope or a function's stack frame, because these two things are roughly analogous, they're quite heavily linked. If I have values in one function's stack frame, those values don't necessarily make sense in a stack frame say, lower down. In a stack frame that is, say, without a reference. Yeah? So we saw when we were dealing with that student example that I had to produce a reference to student to be able to move that reference into a function so that function could manipulate my copy in main of that structure. Yeah? That function needed that information, that reference, to be able to do anything useful. And that is because variables in basically every programming language you will ever see have lifetime. They have a period of time where they are alive. And in C, that's very closely related to their stack frame. And if you remember, stack frames are laid out such that I can effectively stack them on top of each other. So I have my first stack frame down here, then I have another stack frame further up, then I have another stack frame further up again, and I can have references pointing down the stack. Yeah? Those references point down the stack, and the things that are lower down, the values, the variables that are lower down this stack are going to stay alive for longer than the values further up the stack, yes? Because the things further up the stack are functions that will finish, functions that will cease executing. So, a value on the stack will live only as long as the stack frame it is in lives for. And the stack frame it's in lives for as long as that function is being invoked. An invocation of a function sets up a stack frame, sets up its local variables, does some computation, then tears that information down. These values cease to be live. They cease to have liveness. And it's bounded. So here is a really nasty example, and I'll step through this in a moment in more depth. In fact, let's do that now. Let's dump this into a text editor and start playing around with this. And if I'm really lucky, okay. So, here in my program, I'm gonna, let's just step through this part by part. In main, what information do I have? I have the information that makeArray will return me a reference. And apparently also takes a value, which we'll give it, and then it takes that reference and passes it to another value. The only information I have in main is that this has a reference. I don't know anything else about the size or the lifetime of the data. So let's then write a function make array, which returns an int star and takes an initial value, and what it does is it creates an array. It declares an array. And we'll say it's got array size elements. And they're going to set all of those elements to our initial value, while I is less than array size, I will set the ith element to initial, I++. And now what I'm going to do is I want to give this array back. I've set up an array. I want to give this back. This is something that you probably want to do, yes? And you've probably tried doing something like return array. And now we have, oh yes, a problem. And the problem here is that how long is array alive for? Array is a stack variable. Array is an array. Let's try that again without the record scratch. Array is an array that is on the stack. This means what? Its lifetime ends when this function ends. And this function will end when I return. And so if I take my array and I pass a reference to it, because remember I can't copy the array, I would have to pass a reference to the array. If I pass this reference out of this function, I'm going to have a bad time. Because the value is dead. We killed it. It's dead. So let's write our print array function just to show you what that would look like. And once again, we're just going to loop over this array. While I is less than array size, we'll just print out the %d value at array at I, like so. And we need an I++, and we'll print a new line at the end. I'll put a little open square bracket up the top as well, just so it looks a little prettier. Okay, so now we have our two functions. Let's compile these things and let's see what we get. What do we... Let's try that again, but without me making a typo. Okay, the compiler is even warning us about the thing that I'm about to try and do. GCC it. Actually, no, I'll do it with DCC for the moment. I'll also chuck in a hash include of stdio, because apparently I've forgotten that. Damn hash includes, ruining everything. All right. So let me show you that error again, that warning, excuse me, again. Address of stack memory associated with local variable array returned. It's just garbage to us, but we can pull it apart and understand what's going on here. It's telling us that the address of a thing. When you see address of, you can think reference to. A reference to a thing on the stack that is the value of array is now leaving this function. This should be making you very, very anxious, because this should never, ever, ever happen. Because remember, when in my stack frame I return, my stack frame gets pulled apart by wolves. It's torn apart viciously, it's terrible. So back in main, I'm holding a reference to something high up in the stack. What does that reference mean? That reference doesn't mean anything. That reference doesn't have any use to us. So if I were to do something devious, like use that reference, okay, let me show you what this might look like then if I were to print array, because I can print array in make array. After I finish setting up this array, let's see what that looks like. Because this is perfectly legitimate to do. We'll just yes, fine. There you go. So the array is full of 17s. It is completely valid. It is the array we expect, yes, in make array. But now I pass a reference down the stack. I take a reference to a thing that is high up in the stack, and I pass it down, and now it's mangled irreparably in its being torn apart by wolves. So, how do we get around this? Well, there's a couple of approaches we could take. There's the approach we've taken thus far, which is that I move the array. The array is now declared in main. Okay, cool, so let's see what that might look like. And because I'm being nice, I will make a separate copy of this file. So let's move this out of here. Let's move this make array. It's going to take array. But now it also needs to take array size. And now it needs to take our initial value. But conveniently, it doesn't have to return anything anymore. So we'll drop that for the moment. And I'll fix up these names. So I take in an array. What is the parameter for an array? I can just give it square brackets, yeah? Or I can give it a star. It's a reference to a thing. So I can give it array, square brackets that are empty, and int size, and initial. Or I could give it int star array, int size, int initial. Both of these things are effectively the same. Because remember, arrays and pointers are basically just the same thing. So let's leave this as, let's leave this as a reference for the moment. Let's fix up our prototype here. Okay. And let's also fix up print array so it's not doing weird, evil things. And size, there we go. And you can have a copy of array size as well. See how tedious this is. This is terribly tedious. To work out all of the information I need to hold together this structure, to hold together this lifetime. There has to be a better way, I say, and then open a cupboard and they get hit by cans. Size, okay. So, we completely expect this to work because now this data is below, in main. I take a reference to that, I pass that reference up. That's valid, I'm allowed to do that. I can have that reference again and I pass it up again, and that's completely valid because the reference has the lifetime of main. The reference and the value that it refers to have the lifetime of main. Yes? This value here is not just going to disappear whenever a function that I call goes away. This function is alive, this variable, excuse me, is alive for the duration of this program's execution. It so happens. But for any function where I have some value, the functions that that function calls can hold references to that value. That's just a reference going up the stack. It's completely fine. So let's compile this, let's run it, let's see what happens. Hopefully, my compiler warning is, for goodness sake. What are we whinging about here? Okay, fine. Let's get rid of that. Let's get rid of that delete. There we go. Okay. So this should have no compiler errors. And as you can see, it does. And if I were to run it, now I have the arrays I expect. And that's completely fine because these arrays are alive for all of the time that I need them, for all of the time that I use them. These values are alive. Yes? And you could even draw a diagram showing how the lifetimes of these variables move through your program. Another approach,
Yeah, I was going to ask, is there a way to initialize it up here and then move it down?
ooh, is there a way to take a value and move it down? So, when we're dealing with simple objects that we can copy, as in the things we can return, the things we can pass just straight up as parameters, like references themselves, or even just bare values like size, we can just pass those down.
What if you copy each element of the array into one of the arrays?
Yes, I could do that. The problem is that the moment make array finishes, I don't really have an array to look at anymore. Yeah, so the question there was, if I return a reference out of make array, and then I copy those values into an array that's in main, yes, but the array I'm looking at still isn't valid. So, one escape hatch, that's not the way I want to go, one escape hatch that people might, we've talked about taking a lower reference, one escape hatch that people seem to like is global variables. You move the variable even further down the stack, effectively, or to somewhere completely orthogonal to the stack, somewhere where it will live effectively forever. And now we have real problems because, A, the style guide actually has something to say about this. If you haven't read the style guide, what on earth have you been doing with your time? My goodness. Pro tip for dealing with style guides and similar sort of documents that you need to damn well learn. Print it out, stick it to the back of your bathroom door. Works a treat. Here we have the style guides ruling on global and static variables, which are basically don't even think about it. If you do it, you lose marks. Ooh, people sit up and look angry and anxious. If you do global variables, you lose marks. If you do static variables, you lose marks. And we don't say these things lightly. This is a course, I think, where you've noticed that we are pretty chill. We are pretty relaxed. There is not all that much that's really out of scope of this course. You can do pretty much anything. But this is something where you will get badly hurt if you use global variables. And it won't just be us going, yes, you lose marks. It will be you tearing your hair out as you try and work out why the hell your program doesn't work. These are nightmares incarnate in your program. Do not ever, 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 ever use a global variable. And just add a bunch more evers for static variables. These are proper evil. Anyway, back on lighter things. Yes, don't do those things. So, what would I mean by make this global? I just move it outside any of the functions. That's it. That's all a global variable is. It is visible to every single function in my program. And you can see probably why that's a bad idea. A static variable is a variable that I declare as static. And it will remember its value across function calls. Because why on earth not? That's completely and utterly mad. Both of these things are things you should never, ever, 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 ever do. So, there we are. A little bit more permissible, but we'll talk about that later. Largely because it doesn't cause the same problems. Okay, so we have some escape hatches that let us get around this, but like everything else we've seen, where there is some nasty, evil escape hatch, surely there's a better way to do it. Yeah? And there is. Whoa. And this better way to do it is something I hinted at before. It is not to have the values on the stack. Thank you. It is not to have the values on the stack, because if those values are on the stack, well, they have the lifetime problems that any value on the stack has, yes? The stack has lifetime problems, and sometimes they're useful. Sometimes you can live with that. For most purposes, that's completely fine. You can take that sort of problem because it's a convenience. You don't have to jump through hoops just to use variables. So we have this one approach, which is to take a reference lower on the stack, a reference to somewhere that will stay alive for long enough for us to be able to do something useful. And then we take that for the period of its lifetime, because the period of its lifetime is anywhere above this on the stack. So the stack seems like a pretty nasty place to keep this sort of data. And effectively with this approach you wind up just sort of pushing data further and further and further down until, well, it's probably in main, and in your huge multi-thousand line of code system, when you have stuffed every single struct you are likely to want to pass between two functions into main, you have problems. So there has to be a better way. And remember what it is we're looking for. We want values to live for longer than the stack lifetime rules allow. So what if we don't use the stack? What if I were to pull out of my hat somewhere else to keep your data? Somewhere that doesn't have the same lifetime rules, somewhere where you have to explicitly say, here is the thing that we now want to be alive. Here is now when we want it to no longer be alive. It is alive forever between these 2 points. There are no lifetime losses across function calls. There is nothing that could possibly go wrong. The only thing you've got to worry about is losing where that thing is, but if you're careful, you don't. Isn't main its own stack frame? Yes, main is its own stack frame. So we need to put this value somewhere else. And let me say that we have somewhere, whoops, if I can remember how to use my presentation tool. Stop it. We have a better way to do it. And a better way to do it is to introduce this new place called, it's not the good place, stop it, called the heap. So we say now that our memory has at one end the stack, and the stack grows and shrinks over time. It has lifetime rules we have to worry about, all of those usual things. But what if I said we had another region, we call it the heap. It is up the other end of memory. It is just below our program, actually. And in that area of memory, you are responsible for managing that memory. Thank you. You're responsible for managing that memory. So, how do we do that? Well, let me introduce you to 3 new functions. You're probably ever only going to use 2 of them. But I'll introduce you to all 3 because I would be remiss if I didn't. So remember our problem was we want this value to stay alive. Well, let's go back, in fact, let me go back to our original shape of the world, where we had a thing on the stack which doesn't live for long enough. Now what I'm going to do is I'm going to say, yes, thank you, replace that. We'll start with this. What I'm going to do is I want this new value that I'm going to pull out of my hat that's going to be a reference to somewhere on the heap. I want this to be something that will live long enough. And the way I do that is by explicitly asking for some memory, asking for some space for us to put that data. And the way I do this is with a wonderful function called malloc. or memory allocate. I actually don't like malloc all that much, but I'll show you how you would use it because you will see it a lot. Malloc, you give one thing to, and the thing is how many bytes you want. Do I have some way of finding out how many bytes I might want? Yeah! Size of! Size of is literally exactly what I want here. Size of what? Size of, well, let's make an integer array. So it will be one integer times. How many integers do I want? I want 10 of them. This calculation here, by the way, is only done when we run the program. I can ask for amounts of memory that I work out at runtime. There is no requirement that I deal with array size as a fixed value. I can now pull, I don't know, size, some variable size that I might want to pass in. Or I could have that be a local variable. And I'll do that for the moment. And now what I have is a reference. Well, that's kind of boring. I've got a reference, though, to somewhere that is not on the stack. Let me show you what I mean. How do I find out where something is in memory? We saw this last week. Yeah, there is a magic format %p. And if I take this and go printf %p, array is at that, and I'll give it array. But let me also, for contrast, give you a stack variable. Let me give you also, because I so happen to have it, and it's convenient, array itself. I know where array is. It's on the stack. It's in my stack frame. It's one of my local variables. So I can tell you where it is. But I can also tell you where it points, what the value malloc gave me back is. And let's do that. Oh, yes, thank you, person who remembers my hash include forgettery. What's your name? Bob. Okay, we'll go with that. All right, so here is, oh, it compiles. Oh, this sounds promising. Ooh, it works. How lovely. Remember what we are expecting to see. Remember what we are trying to get around. This is what I have. This is what I get when I take a reference on the stack and then that reference now points at a thing that no longer makes sense. Yes? But life 3 finds a way to put those values somewhere where they're not touched. And they're not in main stack frame. We haven't just pushed the problem down. We have pushed it somewhere else, actually. And that's on the heap. And on this system, it just so happens the heap is not as far down as I'd like, but the heap is obviously in a different location to the rest of our functions. Yes? So, there it is. There it is. Now, one important thing to remember is that when you bring a thing to life, this is not a very good metaphor for reality, But when you bring a thing to life, you are also responsible for ensuring it gets killed. Please do not ever apply this to real life. You will be deeply unpopular and possibly also in jail. But what I need to do is say, I no longer need this memory. I no longer need the allocation I have made. And the way I do that is simply by saying, I want to free this. And free is also a function in standard library.h, as is malloc. And for every malloc, you must have an equal and opposite free. Newton's third law of memory management right there. Isaac Newton, very ahead of his time. Newton's third law of memory management. For every malloc, there must be an equal and opposite free. Okay. So malloc is pretty nasty in how I call it. What are some of the problems? What are some of the problems with multiplying numbers together? Because multiplying numbers together can go wrong. Amazingly. What if I have a sufficiently large number that I can no longer hold it in an integer? Well, now I've got a real problem, because this is a signed integer. If it's sufficiently large, this number becomes negative, but malloc expects an unsigned value, and so your sufficiently large value now is trying to allocate more memory than your system has. Malloc also just gives you back a blob of memory. If I were to do, say, print array here, what am I going to get? And for this, what I'm going to do is I'm going to GCC it. Oh man, I hate it when this stuff breaks. Malloc should, anyway, give me back whatever was there before. Because this is uninitialized memory, and if I were to turn on dcc-valgrind, the bane of most of your existences at this point, I'm sure, it will explode telling me this is uninitialized. Whoops! Because malloc doesn't initialize anything for you. It behaves just like me declaring a variable. I declare it, and it's there. So there is another function which we can use, which is called calloc. calloc takes two arguments, number of things, size of each thing. Whoops. Let me keep both of those there. Calloc takes number of things, size of each thing. All right, let's stop there.